Hello and welcome to TidyX episode 103. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes and you can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick and at Tidy_Explain is where Tidy Explained is on Twitter. We are also on Gmail, tidy.explain@gmail.com. You can take out an issue on the GitHub repo or go to our YouTube channel, like and subscribe and drop a comment in the comment section below, and we will get back to you. As always, we appreciate everybody who listens, and if you enjoy what we do and you want to support us, we do have a Patreon page, and we are obviously very grateful for any contribution that you make to our continued work. And here we are at episode 103, which I believe is going to be the last episode of our short series on Bayes, and then I don't really know. I don't know what we're going to move to next. So maybe maybe if you have something you want to see in the comments section, you can instruct us.
You can let us know if you have got any ideas or anything you'd like us to cover. We saw some interesting comments in the past about dates, and if you have any ideas, definitely open an issue on our GitHub page. It's github.com/thebioengineer/TidyX. All right, so we're gonna get going with this. Where the last several weeks we've looked at several different priors that you can use in conjugate pairs, and now we're gonna go through. Okay, you've got the normal conjugate pair, and last week we made the assumption about one of the parameters. How do we go forward from here, Patrick, as I go to share the screen?
Yep. So we've been dealing with Bayes, and we've been dealing with these conjugate shortcuts, which basically allow us to move from a prior to a posterior in a very simple way. And we got to the normal distribution last week. And in order to make the normal distribution, the normal conjugate distribution work, we have to make an assumption about one of those parameters. So remember, like we said last week, in a normal distribution, you have two parameters. It's a two-parameter distribution. You have a mean and a standard deviation. And both of those parameters have their own means and standard deviation. So they have their own measures of center and measures of dispersion. And in order to make the normal conjugate work, we have to basically make an assumption that one of those is fixed in the population, and we want to learn about the other one. So last week, what we did is we said the standard deviation is fixed. We're not going to worry about the variance, the variability around the standard deviation. We're going to fix it, and we're going to learn about the mean. The problem with that is that we sometimes don't know what one of those parameters should be fixed at. And rather, we'd like to take the normal distribution and we'd like to be able to estimate both of those parameters. So we want to make sure that we estimate both of those parameters jointly. And this is a little bit tricky because you end up with a whole bunch of math and integration. And so what really smart people did was they figured out through sampling and through Markov chain Monte Carlo approaches, we could estimate these two parameters in a more simple way. And so we're going to explore one of those types of approaches today. This is Gibbs sampling. And there's a number of different types of samplers. So Gibbs is only one of a few, and it's a very simple one. And so because it's simple, we can code the math ourselves on this. And make it really easy and intuitive to learn. So what we do here is we update the prior distribution with our observations. And then the way it works is as we make that update, we take a random draw from the respective distribution to simulate a single posterior value. And then we do this thousands of times. So we basically have some observed data and we have some priors, and we combine them. And then we take the mean and standard deviation from their combination and we say, give me a random number. And then do that 10,000 times and build a distribution from there. And it's believed that once we look at the distribution and how it all came out, it's believed that that distribution shapes what we know about the data. So let's take a look at our problem statement from episode 102. We remember we had an NBA player efficiency score, a basketball efficiency score, and in the population, we believe it to be a mean of 0 and a standard deviation. I think that's a standard deviation of 1 was what it was last week. So let's make sure we change that so that we're consistent.
Updated.
Yeah. And we'd like to determine the value of a player on our team. So we got a new player and he's performed over 5 or 6 games, and we want to see what do we believe about this player's performance given the performance in the production that we've seen in those 5 or 6 games. And so we're now going to simulate both of our parameters in that joint distribution. We're going to simulate them together. So we need to estimate a prior for both of them. So the mean, let's start out with the mean. Remember, we believe the population mean to be 0, which means it's an average player efficiency score. They're not better than or worse than the average player in the population. And we believe it can vary slightly with a standard deviation of 1. So for our mean value, we have a mu of 0 and a sigma of 1. So what does that look like? We have basically a 95% interval around 0. So if the standard deviation of 1, 95% is a 2 standard deviation. So we have 2 minus negative 2 divided by 4, and that'll give us our mean and our tau, what we're calling tau, our standard deviation. So a mean of 0 and a tau of 1.
Oh.
Perfect. Okay. And the only reason why we could have just set mean to 0 and tau 0 to 1, we could have set that to 1. The only reason why I showed you the math there is because sometimes you don't know the standard deviation, but the prior might be set from a domain expert who says, like, reasonably, I expect 95% of the people to be between these 2 numbers. And then we can use those 2 numbers and do a little bit of subtraction and divide by 4 and get that information. Yeah, correct. Exactly. Could be anything. Exactly. So we have a mean of 0 and a standard deviation of 1. Now the standard deviation. So this is a little bit trickier, and that's why we fixed it in our discussion last week. That's why we made that to be the assumed variable in the normal conjugate, which is what most people do. The standard deviation is tricky because standard deviations aren't normal, right? They don't go below 0. They go from 0 to infinity. So we're going to need to use a distribution that is bounded at 0. And we're going to choose to use the gamma distribution because we've already discussed it in episode 101. There's other distributions you could use. You could use, exponential distributions and chi-square distributions, other distributions you can use. We're going to use the gamma distribution to derive a shape and a rate parameter for our prior standard deviation values. So review episode 101 if you need to remember how that worked. For our standard deviation, we estimate the population to have a standard deviation of 2. And we estimate it to have a 95% interval of about 0.75. So that's 1.25 to 2.75. And so that gives us a standard deviation of 2 and a sigma of 0.375. Remember the little math that we talked about above. We take our little interval, we subtract the highest value from the lowest value, we divide by 4, and that's how we got 0.375. So how are we going to turn this into a gamma distribution? We have a mean and a standard deviation. The first thing that we need to do, the first step, is we need to create a simulation from the normal distribution using our mean and our standard deviation. So we're going to set the seed so that's reproducible for you at home. We're going to take a random draw of 10,000 samples with a mean of 2 and a standard deviation of 0.375. Okay. And then we're going to calculate some basic summary statistics. Remember from episode 101, when we're working with the gamma distribution, we need an alpha or a shape parameter and a beta or a rate parameter. The alpha, the shape parameter, is calculated as the standard deviation of our normal distribution, the average standard deviation of our normal distribution squared, divided by the standard deviation of our simulation, or the variance of our simulation. So it's the average squared divided by the variance. And the rate parameter, the beta parameter, is the average divided by the variance. So average squared divided by the variance for alpha, average divided by the variance for beta, and that gives us an alpha of 27.6 and a beta of 13.7. And as a sanity check, if we divide alpha by beta, we should get our mean. And if we take the square root of alpha divided by beta squared, we should get something that's similar to our standard deviation. And so far, everything checks out. So now we observe some player data. So we have a player. He's performed in 6 games, and he's done relatively well. And so we're going to plug in his efficiency in those 6 games. And then we have a mean and a standard deviation, and he looks to be about a 2.3 with a standard deviation of 1.1. Now, 6 observations isn't very many, and we want to get a better estimate of what we think this player is, given what we know about the population, and enter Gibbs sampling. Here we go. So to do this, there's a few things we need to set up front. The first is we need to specify how many simulations we want to run. In this case, we're going to run 11,000 simulations. And really what it's going to be is 10,000 simulations, because the first 1,000 are going to be the burn-in rate, or what some people call the wind-up. And basically what we're telling the simulation to do is saying, hey, we know it's going to take you a little bit to really learn about this data, so we're going to give you 1,000 observations to learn, and then we're going to start counting. And we're going to derive our parameters from there. So we're going to set our burn-in rate to be 1,000. Some people do 5,000. It just depends on how much computing power you have and how many simulations you want to take.
Yeah, and this is a pretty common concept from like mechanical engineering too, where you'll get like you need to burn in your brakes in your car. You need to get them to be warmed up and be used a little bit before you really want to work them really hard. So that this is kind of a terminology comes from other practices, and it's kind of fun to see this being applied here as well.
Yeah. So we create our end simulations and our burn-in rate. So make sure we run. I don't think you ran those yet. Oh, yeah.
Nope. There we go.
Then we specify our priors. So remember, we have a mean and standard deviation for our mean, and we have a mean and standard deviation for our sigma. But remember, they're alpha and beta because we're working with the gamma distribution. And then we have to get some information out of our observed data. So we're going to calculate the sum of squared error, which is the sum of the squared error. So we have the error, which is the observed score minus the mean of the scores squared and then summed up. We're going to get the mean of our observations, which we saw before was around 2.1. We're going to get the number of observations, which is the length, which is 6. And then we're going to get the variance, which is going to be our sum of squared error divided by our number of observations. Okay, and now we're ready to run our Gibbs sampler. We're going to set up some empty vectors to collect the results of each of our 11,000 simulations. So we're going to be simulating jointly, remember, a mean, a mu, and a posterior sigma, a standard deviation. Both of those are all NA. They're just waiting to be filled. And now we run our Gibbs sampler. So we're going to specify this in a for loop. For I in 1 to number of simulations, which is 11,000, there's 3 steps, and then we save it and we repeat those 3 steps. The first step is we want to calculate precision, and precision is calculated as the number of observations we have, which was 6, divided by the variance of those observations, plus 1 divided by the standard deviation of our mean, our tau. Okay? Then from that precision, we move on to calculating the mean of our simulation. So we have our mu is going to be the mean of the observations weighted by the number of observations divided by the variance of those observations. And then we add to that the mean of our prior divided by the tau of our prior, the standard deviation of our prior. And then we're going to divide all of that by the precision, which we calculated up in line 107. That's the mean, and then the standard deviation for our mean is calculated as the square root of 1 divided by precision, which remember from the last episode, precision is 1 over the variance, so this is how we get it back to being standard deviation. And then we take a sample. Here's where the Gibbs sampling comes in. We've calculated a mean and a standard deviation for our mean, and we're going to run this R norm. We're going to take a random normal sample of 1, from the mean and standard deviation, and we store it in mu. Next, we're going to look at our other parameter, which is the standard deviation. We have a shape parameter, which we're going to combine with our prior. So we take the standard deviation of our prior plus the number of observations divided by 2. For the rate parameter, we take the standard deviation of our standard deviation. We add to it the sum of the squared errors divided by 2. And then remember, we're working in this gamma distribution here for our standard deviation. So we're going to do 1 divided by our gamma, which is a random draw from the gamma distribution. We're going to take 1 draw. We're going to pass it our shape parameter that we just calculated. We're going to pass it our rate parameter that we calculated. And now we have sigma as an inverse gamma distribution. So if we take the square root of that, we're going to store that in this posterior sigma. That's going to be our posterior standard deviation. And the mu that we calculated, we're going to store that in our mu. This runs super fast. And now we have 11,000 posterior means and standard deviations. We're going to minus the burn-in rate, so minus the first 1,000, which we specified earlier. And now we have posterior distributions. So let's take a look. Yeah, there we go. So now we can take a look. Ellis, you want to walk through some of the plotting here?
Sure thing. All right, so first we're going to set par. So this is going to set our graphics to tell them what we want to do. So this is saying we want to have two plots, one right next to each other. We're going to use the hist function, which is producing a histogram. So we're going to get a histogram of mu, the posterior mu, and the posterior sigma. So we're going to run that. Oh, no, I need to run that first, then that, then this. So here we go. We get a quick look at the posterior mu. So this is the the histogram of our mu, and this is the posterior of our sigma. So you can kind of see how that's moving around there. Next, we're going to take a quick mean of our mu and sigma, just so we can kind of take a look at that. So this is where, on average, we think the player will be. So we're thinking the player will be about 1.92, which is, higher than 0. So we're expecting them to be around a 2 with...
but not as high as the 6 observations that we saw, which were at like 2.1 or something.
Yeah, here, let's just do a quick mean of obs. Is it observed?
I think it's obs efficiency.
Yeah, 2.25. So we don't think he's quite as good as 2.25, but we're not saying that they're not going to be very good. Yeah. We can take a quantile as well, so we can look at the range of the mu and sigma. So we think they'll be somewhere between 1.16 and 2.67, with a standard deviation of 0.63 and 0.90, somewhere around there.
Mm-hmm.
Then we can do some trace plots here. So here we're going to look at the actual predicted values, posterior mu and posterior sigma. So we're going to quickly call dev off to clear that out. We're going to once again set it to be, we want to do plots, but this time, as you see, this is 2, 1. So this is going to be stacking them as opposed to having them landscape. So plot this one, plus that one, and I'll let Patrick explain more on this.
Yeah, so these are two plots that people use to diagnose the how well their simulation did. And this is, you can see it's just like random jitter around our means for both the mu and the sigma. Richard McElreath calls them furry little caterpillars. But basically, if your simulation had an issue, the trace plots would look really weird. Like they might start out a certain way and then like just shoot up straight into oblivion. They won't look totally normal like this. And this is what we want to see. And we also notice that in some instances, like just over 2,000 on the blue, there's like this high spike. And that's just the simulation basically pulling a random draw and exploring that large feature space. But for the most part, it starts to constrain itself around something that it feels to be representative of the data that we've observed combined with our prior knowledge of where we think that data is. And so obviously if we changed our prior, these plots would shift, but they should all look like that random kind of furry caterpillar. And that's one of the diagnostic plots that people often apply. And then another way of showing the posterior mu and sigma is to just do this joint plot. So we're going to plot them on an XY axis. And so obviously the density of the data where it's clustered in the middle is going to be the most likely mean and standard deviation for this individual's performance. And of course, we can also show this with a histogram by taking what's called sampling from the posterior. So here, we're going to use that sample function that we talked about in the first episode of this series. And so what we want to do first is sample from our simulated mu values. So we're going to say sample from posterior mu 1,000 times, and we're going to sample with replacement. So we're going to pull a marble from the jar and put it back so that it has an opportunity to be pulled again. And we're going to do the same thing with our standard deviation. So now we have two samples, a posterior mu and a posterior standard deviation, and then we're going to combine those, 100,000 times, in a normal distribution, and this is going to represent the player's mean and standard deviation of their performance. And you can see in there, there's some values that are negative, some values that are really high, some values that are closer to zero. This is great. It just means that we're pulling from this large distribution that we simulated. And now we can plot this and look at what we think for the athlete. So we can plot first their posterior sample. So this is what we just created, and that's going to give us a density in red. And then we can plot a few bits of information that give it context. So the first one is, what's the mean of that posterior sample? So boom, great. And then we can plot the one standard deviation above or below, or you could do 2 times the standard deviation if you wanted to do 2. But this gives us a look at our player. So mean and 1 standard deviation, that's their distribution. This is how good we feel our player is, based on our first 6 observations and our prior knowledge about what we believe players would normally be within this league. And as we get new data, we can continually update this, and it'll shift up and down a little bit until it settles into something that's normal for the player. So that was like 40 lines on Gibbs sampling. If you don't want to do all the math by hand, Jim Albert, who's a Bayesian statistician and professor at Bowling Green University, wrote this great book called Bayesian Computation with R, and it has this nice package called Learn Bayes that is a supplement to it. And so he has this function called normal post sim, where you pass it your observations, observed efficiency, and you pass it your prior in a list form. So you pass it the prior mu, which we calculated above, our mu and our tau, and you pass it your prior sigma, which is your alpha and beta, because you're dealing with the gamma distribution, which we calculated above. And if you do that, you'll get something very similar. Remember, these are random draws, so it'll come out close to, but not exactly what we saw above, but about 2.1, posterior mu 1.9, and posterior sigma 0.75, and so that's pretty,
next to each other.
Yeah,
there we go.
It's pretty close to what we saw with our mean and our mu and our posterior. We're right around the same. And so if we did this again, we would get slightly different values. But this is a way of doing what we just did in 40 lines in 5 lines.
Yeah, see, I just rerun this a couple times.
Yeah,
and we've gotten
rerun it a couple times.
values.
And it's always going to come out relatively similar.
Yep.
There you go. And so that's how you can write your own Gibbs sampler and play around with priors and observe data and see what you can learn about your posterior.
Well, there you go. So maybe we should start applying this to figure out what people want to watch, or they can just comment down below.
Yes, that's a good idea. Or they could just tell us what they want to watch.
Exactly. We love that. All right, so I think that was a great series on Bayes. I know I learned a lot, and I hope now I have a better idea of how to conceptualize this and talk to other people about this, and I hope everyone else did too. Thank you all so much for joining us for this series. And as always, keep on exploring your world. Patrick, you want to do our sign off?
Yep. Well, he's Ellis at Ellis Hughes on Twitter. You didn't even say yourself.
I'm not important.
And my name is Patrick Ward. I'm on Twitter at OSPPatrick, and the both of us are on Twitter at tidy_explained. Tidy.explained@gmail.com is where you can drop us an email. You can also take up an issue on the GitHub repo. You can go on YouTube, like and subscribe, drop a comment in the comment section below. And as always, if you appreciate our work and you like what we're doing and you want to support us, we're always thankful for anyone that does that. And our Patreon page is open. So, please visit that if you feel like you'd like to.
Thank you all so much, and keep on exploring your world.